All right, so just as a reminder, class on Friday is going to be a video that I'll put on YouTube. I'll post the link on Blackboard so you'll have it there. And we won't have any in-person class meeting on Friday, but we will get back to our normal schedule here in the classroom on Monday. And then Wednesday of next week is when homework number 4 is going to be due. That'll be due before class, and it's related to some topics that are going to be covered in today's class and Friday, water chemistry effectively. So we're moving to chapter 5 in the book, and I'd encourage you once again to use that as a resource. It's just simply not enough to listen to what I'm telling you. You have to have some additional exposure to the material in order both to retain it and also to understand it with adequate depth. So you should be reading the book, and if you're not, then you can't expect to succeed. So today we're going to be moving on to water chemistry. Does anybody have any questions related to the announcements before we start talking about water chemistry? All right. So here is a picture of something that you might have seen before if you have soft water at your house. A lot of places, particularly when they use groundwater in the home that has a high hardness, high hardness in water makes it so that clothes don't feel as soft, so that soap doesn't lather as well. And so it's not a matter of health, it's just a matter of maybe aesthetics and preference to have soft water rather than hard water. And one of the ways that people can, in their own home, treat water to remove hardness is by using sodium chloride. And so this is just the tank of rock salt or pellets. You'd need to put it in there. Typically people would put a bag of salt in there every month, and then it gradually becomes depleted as the ion exchange resin needs to refresh itself. We'll talk more about softening and the effects of water hardness, but this is just an example of how pretty common and innocuous chemical sodium chloride is used in water treatment. In broader scale applications, like in a municipal water treatment plant, there's a wide array of chemicals that get used. And so being able to understand chemistry is critically important for water treatment because we're adding all sorts of things for different purposes. For example, if you attended Dr. Yo's presentation, then you heard her talk about ferric chloride and alum. And so those are both coagulant chemicals that can be used to destabilize colloids and improve the turbidity of water. Sodium hydroxide would be used as a tool for changing the pH of water. Sometimes we need to adjust the pH in order to improve the performance of coagulation and flocculation. Sometimes we need to adjust pH just because otherwise the water would be corrosive or prone to scaling. So chemicals like sodium hypochlorite, chlorine gas, and chloramine, those three chemicals are used to disinfect drinking water after it's finished and provide some residual protection against water getting dirty again. Is leaving a little bit of chlorine in the water after it leaves the treatment plant makes it so that if there was just a small amount of contamination in a pipe, then the residual chlorine would be able to break that down and ensure that people don't get sick. Chemical like soda ash would be used in removing hardness. It could be used to adjust alkalinity of water. And things like phosphate and lime are used as corrosion prevention because depending on the pH of the water and the amount of alkalinity and hardness in it, sometimes the water has the tendency to scale, which is that it would lay down mineral deposits inside the pipe. So phosphate can use to prevent scaling. It keeps those minerals dissolved in water that otherwise would begin to precipitate. And lime is also used as a pH adjuster. And finally, ozone is an example of a chemical that could be used either for disinfection or for other things as well. Ozone is an oxidizer. Ozone, by the way, is just O3. You know that right now we're breathing O2. Ozone is O3, and it's not really stable. You'd recognize the smell of ozone You've smelled it before, I bet, when using maybe like a hand mixer or a blender. Sometimes when you're using electrical devices, there's just kind of like the smell of electricity. That's ozone. And ozone is intentionally generated in some drinking water treatment plants, either to kill bacteria or to improve the taste and aesthetic properties of water. So there's a lot of things we want to control to make drinking water more pleasant and more safe. We also need to control things in wastewater treatment to prevent environmental contamination. And so chemical addition is one of the biggest tools that we have in drinking and wastewater treatment. So we have to have just some basic tools to be able to calculate and design. And so that's why you take Chemistry 1 and Chemistry 2. It's partly for the environmental applications, but of course there's also chemistry in materials like concrete and steel. You need to know a bit about chemistry for that. One interesting thing on the subject of taste, some drinking water tastes great. Some drinking water tastes terrible. Even though it's safe, it doesn't taste very good. So taste is a subjective thing, and there is a competition held each year, believe it or not, here in West Virginia. It's an international competition that's held in Berkeley Springs each year. It's the Berkeley Springs International Water Tasting event. And people come from all over the world to taste water. And you can see the judges get all dressed up, and then they've just got glass after glass of water in front of them. They do kind of like a blind taste test so that they don't know whose water they're evaluating. They just, they say what they like, and then they grade it. And they have different divisions. There's like a division for tap water. There's a division for bottled water. There's a division for carbonated bottled water. And so it's interesting to see who is the winners. Santa Ana, California had the best water in 2024. And they're a previous gold medal winner as well. So they consistently have good tasting water from year to year, and it's different judges. It's not always the same judges. Closer to home, Montpelier, Ohio, has been an award winner again in lots of prior occasions. And so closest to home, Harper's Ferry. Anybody here had the water in Harper's Ferry? What does it taste like? Like water? Yeah. I've never been over there before. Is that in the Eastern Panhandle? Yeah, so that's not really West Virginia, right? That's more D.C. Yeah. So it kind of makes me want to, number one, go to this competition, and I want to wear a tuxedo and drink water. I imagine they have, well, I was going to make a joke about their toilets, if they're sitting there drinking water constantly, but I don't know. They need to have the toilet competition right next door. It's an international competition. You can see that there's like some bottled waters from Greece, Canada, Australia, but USA had the best tap water. That must just be because other countries aren't participating, because I've had some delicious water in Switzerland before. They don't use any chemical disinfection there, so you don't have that residual chlorine taste. In Switzerland, they don't need to, I guess. It's just perfect glacier water or something. But we'll talk a little bit about the aesthetics of water and how you manage taste and odor and color of water. It's not, the color of the water isn't something that is inherently dangerous, but people don't like it. When orange stuff comes out of the tap, people get really freaked out. And it may just be, that sometimes they'll flush fire hydrants in part of town just to make sure that the valves aren't plugged. And when the fire department does that, occasionally just some precipitated, it'll usually be like a little bit of rust effectively, or sometimes manganese will settle and precipitate in water. And like people are like, black stuff was coming out of my tap. Well, it's just manganese. It's not necessarily going to make you sick, but it really bothers people when black stuff comes out of the tap. Some black stuff coming out of the tap maybe wouldn't be great. Like if you live in a place where they're fracking the water, and it could be oil or bad fracking chemicals. But we'll get into all of that And we need just some, let's do a refresher on water chemistry. You maybe remember from your previous chemistry classes that 1 mole is defined as 6.02 times 10 to the 23rd particles. And what's this number called? Avocado's number, right? Avogadro's number, yeah. So I don't know why it's that number in particular. I don't know. Maybe they just said, you know, like we're going to define a certain mass of something as a mole, and then they, after that, assessed how many particles that ended up being. So probably something else was the baseline, and then the number of particles was like a secondary reflection of that earlier baseline. And so the molecular weight is the number of grams needed for 1 mole. And molecular weight and atomic weight is the same thing if you're just talking about a mole of one element. But when we have combinations of elements, then it's different. So for example, a mole of hydrogen, the atomic weight and molecular weight would be the same, because if we're just talking about hydrogen. But then when there's combinations of things like calcium carbonate, we'd talk about calcium carbonate in terms of its molecular weight because it's a molecule, a combination of atoms. So it's just how many grams is needed for a mole of something is the molecular weight. Now, an equivalent is very closely related to a mole, except for that instead of counting the number of particles, we're counting the amount of charge or the number of functional units. And so iron, just as an example, Fe, can have either a +2 charge or a +3 charge. And so if we were going to talk about equivalence, then we'd not only look at the number of particles that were there, but then we'd also look at what charge does the iron have. Does it have a +2 charge right now or a +3 charge? And so equivalent is taking into account the charge that's present. And so closely related to the molecular weight is the equivalent weight. EW is equivalent weight. And that's just the number of grams needed for 1 equivalent of something. So I have a handout for you where we're going to do some basic calculations just to get the mental chemistry juices flowing here. Let me bring it up on the screen for the benefit of the sizable fraction of your classmates who aren't here today. All right, that's not it. That was reactors. This is it. All right. We're going to do this first question here. Let me give you the paper. And the periodic table's on the back side of the paper. Okay, so I'm asking you the mass of iron required for a mole, how many iron atoms are there per gram of iron, the mass of iron 3 required for an equivalent, and how much charge is there in 1 gram of iron 3. So let me pause. I just want to see what you can do. You can collaborate, check your answers, chat with people, just double check, and then we'll go through it together in a couple of minutes. All right, so part A asks, what's the mass of iron required for a mole? So if we go to the periodic table, zoom in on iron. Okay, iron, it says here on the periodic table, 55.845. So that means that you need to have 55.845 grams of iron for there to be a mole of iron particles. So that's just talking about, 6.02 times 10 to the 23rd iron molecules. To get that many molecules, you have to have 55.845 grams of iron. So that's part A. Just looking it up straight from the periodic table. So now, this is asking how many iron atoms are there in a gram of iron. So if 55.845 grams is equal to 6.02 times 10 to the 23rd particles, then we can divide the number of particles by the number of grams, and then we find out that there's 1.08 times 10 to the 22nd atoms per gram. So a lot of this is just going to be looking at the units. And what do you divide with what? Sometimes you have to evaluate that by just looking at the units of what you know and what you're trying to find out. So 1.08 times 10 to the 22nd atoms per gram. Now we deal with the charge. So iron 3 has a +3 charge. So how much mass is required for an equivalent? Well, what we're recognizing is that in a mole of iron, there's 3 moles of charge. So if it took us 55.8 grams to get 1 mole of particles, we only need 1/3 that amount of iron to get 1 mole of charge, because each mole of iron has 3 moles of charge. So it's 1/3 the quantity. And then the last part here, how much charge is there in a gram of iron? Well, we knew that a gram of iron has this many particles, and there's 3 units of charge for every unit of particles, and so it's going to be 3 times as what we calculated for part B. Or to look at it in a more fundamental way, a mole of charge divided by how many grams is needed for a mole of charge tells us that in 1 gram there is 3.23 times 10 to the 22nd charged particles in each gram of iron 3. All right, so that's just kind of revisiting the ideas of molecular weight and equivalent and so on. Did anybody have any questions about that first part? Okay, so molarity is now where we're taking the number of moles and dividing it by the volume of solution. So it's essentially a concentration. So moles is an absolute amount. Molarity is how much of that amount is in a certain volume of solution. So in the next question on the in-class exercise, it says that we've got a solution with 1,710 grams of H2SO4 per liter. So we want to know the molarity. So what you're going to have to do is find out if this is the number of grams of H2SO4, how many moles of H2SO4 is there? And we do the same thing as before, where we look at the periodic table. So if the compound we're interested in is H2S04, start with the hydrogen, 1.00794. So 1.00794. There's 2 of those, plus 1 sulfur. So sulfur is 32.066. 32.066 plus now 4 oxygens, and oxygen is 15.9994. A lot of times when I'm feeling maybe not lazy, but when I'm feeling a little lazy, I just say 16 instead of 15.9994. Or I'd say 1 instead of 1.00794. But let's be really precise here. Calculate what is the molecular weight of H2SO4. So it is 1.00794 times 2 plus 32.066 plus 4 times 15.9994. I got the molecular weight of H2SO4 is 98.07948 grams per mole. Okay, so if that's how many grams of something we need for a mole, I've told you in this next thing here, what is the molarity we want to know, and what is the normality of this solution? So I haven't told you about normality yet. Let's just look at the molarity. So we want to find out how many moles that is. So the number of moles is 17.44 moles of H2SO4, and we were told how many grams there is per liter. So that just makes it 17.44 molar. Capital M means moles per liter. That's the molarity. Now, the next thing is the normality. And the normality is how many equivalents per liter of solution. Okay, so this solution we calculated was 17.44 moles per liter. So that's how many, like if we're counting the particles of H2SO4, there's 17.44 times 6.02 times 10 to the 23rd. Now, when it's asking about the normality, what do you think it's asking about? Remember, normality takes the number of functional units into account. So when you put H2SO4 in water, it doesn't just stay together as a single molecule. What it actually does is it dissolves into 2H plus and SO4 2 minus. So when it's asking what's the normality, it's effectively asking how many particles of hydrogen are there per liter of solution. So we have to just like kind of instinctively know what it's asking about. There's a factor of 2. There's 2 moles of hydrogen for every mole of H2SO4. 2 active units. And so the normality is twice the molarity. So then the normality here is 34.88 normal, capital N. So that is talking about how many moles of charge or how many moles of hydrogen. So for an ionic compound like H2SO4, you have to know a bit about how it's going to dissociate when it's dissolved into water. Okay, so any questions about molarity or normality? Now, you may remember that the definition of pH is the negative of the log base 10 function of the hydrogen ion concentration. So the brackets, these brackets means the concentration of hydrogen ion. So when we add H2SO4, it dissociates into 2 hydrogens plus an SO4 2 minus. And an acid is defined as a compound that releases a proton. A base is one that accepts it or neutralizes it. So this next problem on our in-class exercise, let's say what if we had 100 milligrams of H2SO4 and it makes a liter of solution. So what's going to be the final pH? So to know the pH, what we're trying to find here is the hydrogen ion concentration. So let me pause for a second. I'd like you to try and tackle this one. What you need to do is you need to find out what is the concentration of hydrogen ions. And the concentration of hydrogen ions is going to be the number of ions per liter. That's what we're talking about with the concentration. So you need to know what is the number of hydrogen ions it disassociates into when it's dissolved. So we want to know the molarity and the normality in order to put it into the negative log of the hydrogen ion concentration. And H2SO4 still has the same. What did I have before written as H2SO4? The molecular weight? 98.7948 grams per mole. All right. We're still working with H2SO4 in this third problem.
I think it's 98.079.
Ah, thank you. There we go. Okay, so here's what happens if we dissolve 100 milligrams of H2SO4 in enough water to make a liter of solution. So what that is 0.00102 molarity. And then since you get twice as many hydrogen ions, then the concentration of hydrogen ion is 0.00204. And if we put that into the log function, multiply it by -1, then the pH is going to be 2.69 of that solution. That's the final pH. So now we have to figure out how much sodium hydroxide would be required to neutralize it. And hint, it's not 100 milligrams. We want to neutralize that H+, and we're going to neutralize it by using OH. And so here's the neutralization reaction. I've written it at the top here. If you've got H2SO4, which is dissociated into 2 hydrogens and this sulfate, then you're going to need 2 hydroxides to neutralize the 2 hydrogens, because the hydrogens combine with the hydroxide to form water. So like the balanced reaction is that 2 sodiums and 2 hydroxides, which is what it disassociates into when you put the sodium hydroxide into water, will neutralize the 2 hydrogens, form 2 waters. Okay, so to neutralize, it's a 1-to-1 ratio of hydroxide to hydrogen. So what we want to do is we want to deliver enough hydroxide in solution to neutralize 0.00204 moles of hydrogen. So that means we need 0.00204 moles of sodium hydroxide. And we can look up the molecular weight of sodium and hydroxide. So here it looks like I did the lazy way. 16 instead of 15.999. 1 instead of 1.007. So anyways, the molecular weight of sodium hydroxide is approximately 40 grams per mole. So then what that means is if you need to have 0.00204 moles of hydroxide to neutralize the hydrogen, then that means you have to add 0.0816 grams, which is 81.6 milligrams. So what we had is we added 100 milligrams of H2SO4. It brought the pH down to an acidic range, and we want it to be back into balance. The balanced range, that neither acidic nor basic, is 7. And so we disturbed that initial equilibrium by adding the H2SO4. It brought the pH down to 2.7. And we can restore it back to the neutral range by neutralizing the excess hydrogen. So we need the same number of hydroxide particles as there was hydrogen particles, and we can get that number of hydroxide particles by adding 81.6 milligrams of sodium hydroxide. Any questions about this third question on the in-class exercise? Okay, well, that's all I have for you today. Just remember that class on Friday will be posted on YouTube. I'll put the link on Blackboard when it's available. It'll also send you a message to your email. So let me know if you've got any questions, and otherwise I'll see you back in class on Monday.